again, thank you for spending your valuable time with us today. Today is all about showing you the differences between two types of sensor technologies, and we generally call these cooled and uncooled cameras. And Andrew has a little presentation that we'll go through afterwards that really just gets to the kind of the core differences between those. But what I wanted to do is just introduce you also to some of the future webinars that we're going to do. So obviously at the moment we're on webinar number 1, the cooled, and then what we're also going to do is webinar number 2, sync and trigger. So this is really about synchronizing your data with other pieces of hardware. So for example, it could be a visual camera where each frame of the thermal camera is taken at exactly the same time as the visual camera. Or it could be syncing it to an object that's moving. So for example, if you imagine a jet turbine blade, every time the same blade comes around, it pulses, and then the camera takes a picture at that particular point. So this is going to be actually one of my favorite topics. So we're going to be looking at that. And then really what we want to do is we want to talk about some of the applications and understanding how people use the cameras, and we're going to delve into PC circuit boards. So this is a great one. So it shows you how we use the research software to really get in and find tiny little temperature differences using filter things like we can do subframing, and we can do lots of different image tracking within the software. So for circuit boards, the hardware and the software is really, really important. Outdoor one, which is one of my loves as well, is long distance imaging with some of the big range cameras, and how we select the right lens, how we deal with atmosphere and environmental conditions, and even down to simple things as how do you power cameras in the middle of a field. Next one, high-speed imaging. So we often get customers asking for a high-speed camera, but really we need to understand what that means. So this one will be understanding, do you mean 1,000 frames per second, 10,000 frames per second, or do you actually need one frame taken instantaneously? So for example, in the example of a jet turbine with the blades going round, it's one frame now, one frame now, one frame now. So it's a really understanding the terminology and what the hardware that we can do. And then we're going to end the series on webinar 6, the hidden gems. So these are things that we use to help sell the cameras to customers to help their application. So this can be filters. So for example, filters could be a CO2 filter. So you can put a CO2 filter into the camera, and then you can see different gases. We also have reference sources. So if we want to understand, does the atmosphere change the temperature readings of the object we're looking at, and using a black body to understand how atmosphere can change that and how we correct for that. And even down to things like different tripods. Unfortunately, even nowadays, we have people buying very expensive cameras, but very cheap tripods where you can touch the floor, the tripod wobbles, and you're getting a blur and a wobble on the screen. So we're going to talk about heavy duty tripods, mounts, really to get the most out of it. And that's going to be 6 webinars, and we think it's going to be great fun. So we hope that everyone here today will enjoy today, and then will also join us for the next 5. So I'm just going to stop sharing that, and then I'm just going to flick to my other camera, and then we'll just show you very quickly the types of cameras we're talking about. So in the screen, we have 4 cameras, 2 of which are cooled and 2 of which are uncooled. So for those unfamiliar with the cameras, we have a FLIR A70 and a FLIR A700, and these would be what we would define as uncooled cameras. And then we have the FLIR A6750 and the big premium X series, and these would be cooled. So one thing that you can obviously see from here is there's a big size difference, and Andrew will go into some of that. But essentially, inside the cooled cameras is a Stirling cooler, And the easiest way to think of that is literally a fridge. And the fridge is cooling the sensor down to minus 100, minus 200 degrees to remove a lot of the noise in the sensors. So you end up with a razor sharp, crisp image. But Andrew will go into that info. So if we just come back to mine. Please just leave any questions towards the end, and we'll have a little Q&A session, and then let's hope you enjoy it. So just introduce Andrew. So Andrew's going to go through a little presentation. So over to you.
Right, thank you, Matthew. Nice little intro there. So I'll share my screen now. Okay, so if I go into... Is that showing up okay for everybody? Can you just confirm that, Matthew, that's being shared properly?
Yeah, that looks good.
Fantastic. Okay, because I'm blind here now, the screen's got the PowerPoint on it. So again, thank you for everybody for joining. So today, the first webinar, I say, is going to focus on the difference between the cooled and uncooled technology. But first, I thought it would be useful just to kind of go back to basics with what we're talking about when we're talking about infrared and temperature measurement and the kind of factors that we take into consideration before we get to uncooled. I think there's somebody's mic on there. If I can just turn the mics off, please. So yeah, I'll go through the technologies, and although some of the webinars will focus on specific applications, I'll kind of briefly go over some of the useful applications that we use for, so material science, PCBs, and some of the things that Matthew has mentioned as well. And I say at the time, we'll hopefully have some time for some questions. And if we can't get through them all, as Matthew said, we'll come back to you later on after the presentation. So first of all, just to tell you a little bit about who we are and FLIR. So if you've not heard of FLIR, they are the industry leading manufacturer of thermal cameras in the world. So they started off in the defense sector and still are so at the high end, they are the leading manufacturer. Thermal Vision Research, which is our company, so there's me, Matthew, and recently Jeffro joined us too. We have a premium technical partner of FLIR in the UK. So we focus purely on the high end science cameras. And not myself, I've had a couple of years experience, but Matthew's had over 10 years experience working in research and development and science applications. So we work across lots of industries, including the military, aerospace, all kinds of research projects in academia, semiconductor technologies too, automotive industry, whether that's kind of engines or whether it's EV, and more recently as well, more the additive manufacturing side of things, NDT, material science. There's probably, I can mention 20 more of applications, but there's a lot of applications that we can that we deal with. One of the things that sets us apart from other companies is that we provide on-site application-specific demonstrations. So a lot of the cameras we sell are quite expensive and very specific. So we always make sure that the camera can do its job before we actually sell that. So, and we do training days as well. So if this, after this presentation, if this is something that's interest, by all means get in touch, and that's something that we can arrange. As well as selling the cameras, we also do hire and lease options too. And another thing that sets us apart in terms of technical support, we provide technical support for life. So if you buy a camera from us, you can always give us a call, send us an email, and we'll always support you the best we can. Anyway, so on to the next. So I won't labour on this too much. You've probably all seen this, remember it from school, but it's just to really show where the cameras operate in the infrared spectrum. So most cameras that you would come across in day-to-day life in your work might be long-wave cameras. So these are the microbolometer technology, and they're in the 7 to 14 micron. But the cooled cameras that Matthew briefly showed, they operate in the mid-wave with a few exceptions. There's a lot more contrast in there if you looked at the Planck curve, so they can be much more sensitive. And also there is shortwave infrared too, which are for very specific applications. So in the shortwave, there's not too much energy emitted at low temperatures, so they tend to be used for high temperature applications, usually 400 degrees and above. But generally, when we're talking about the cameras, the cooled cameras are the mid-wave, and the long-wave cameras are the uncooled cameras. So just a a bit about what it actually means to measure temperature and the relationship with infrared. So it's a misnomer, but often people think they can get a thermal camera and it's a thermometer. It's not a thermometer. What it does, it measures IR energy that's been emitted or reflected by objects around it. So all objects, everything emits infrared energy in the form of infrared. And this is, depending on the frequency, is proportional to its temperature. So temperature will increase with IR energy intensity, whether that's in the long wave or the medium wave. And measuring this emitted IR allows temperature to be measured. However, unless something is an ideal black body, not all the infrared energy emitted is proportional to the temperature of the object that you're looking at. Some of it will be reflected. So first, just go through a couple of definitions. So perfect absorption. So a black body is a theoretical object that absorbs all radiation that falls upon it, and no radiation is reflected from its surface. This is ideal because it doesn't exist in the real world. And also as well, complete emission. So an ideal black body emits radiation across all wavelengths, and this emission is known as black body radiation or thermal radiation. And the intensity and distribution of this is solely dependent on the body's temperature. In the real world, though, objects are never an ideal black body, as I just said. So we must know what the emissivity value is before we can measure the correct temperature. Oops, no. There we go. So this is just a very simplified diagram, really, of what happens when the camera is looking at infrared. It cannot differentiate between reflected and emitted infrared. So, for example, here, if you've got the sun, a source of infrared, that will also be heating both objects there, in this instance, cars. And the infrared from one object will be reflected onto the other, which will then also be reflected onto the camera lens and then onto the sensor and actually influence the image that we see at the end. So the equation there shows that the emissivity is a kind of like a scalar value that determines what the temperature will be. And this is a value between 0 and 1, and it's unitless. So we need to know this value before we can accurately measure the temperature. So the emissivity of material is determined by its surface properties. So something that's polished and shiny, like aluminium, will have a very low emissivity and a high reflectivity, whereas something that's quite have a kind of like a matte finish, something like human skin or wood, will have quite a high emissivity. Again, it's unitless between 0 and 1, and the reflectivity is the inverse of that. A simple way to calculate the emissivity is by comparing the camera reading. So you'll have a reading on the camera of the temperature of an object. If you then use a thermocouple or some other temperature measurement device, a contact measuring device, you can correlate that with the camera. And by adjusting the emissivity in the software of a camera, you can calculate the actual exact temperature. Once the contact measurement is removed, you can then be sure, as long as the surface property doesn't change, like it doesn't melt, and the surface, the surface property stays the same, then you don't need to change that emissivity value again. I don't want to labour the point too much with emissivity, because in most applications, what the engineer is looking at is a change in temperature, so a relative change, or the difference between two areas. The emissivity does not affect these readings. So even if the emissivity is not correct and your temperature may be 2 or 3 degrees out in terms of absolute temperature, this won't affect relative temperature measurements. So if you want to measure one spot in relation to another, the emissivity value won't affect that. You will still get accurate relative temperature measurements. Just a table here, just to kind of give an example of some of the common emissivity values for materials. so common there, like metals. You can see polished and treated metals have very different emissivity values. So it's not the material itself, it's very much the surface property of that material. Just a bit of a disclaimer as well, this is for long wave cameras. If you have a medium wave camera, these emissivity values will change because they don't emit across the spectrum the same. They may emit in the mid wave differently to in the long wave of the spectrum. As well as emissivity as well, there are other factors to consider. Most of these in a lab environment won't have much bearing at all on the absolute temperature. But if you're working with very hot objects nearby, or you're working in low room temperature environments, you need to consider the ambient temperature as well, and the reflected temperature of objects around you if you're in the lab. As well, if you're outside, the distance from the object can come into consideration because the atmosphere with a lot of moisture in it attenuates the infrared energy. So, and that is why humidity is also a factor as well. But when you're working at 10 meters, less than that, you're not going to notice any difference at all. So these are just other things that you might want to consider. There's also transmittance. So some objects are partially transparent to IR. These materials are not really appropriate usually for using for R&D applications, but it comes into consideration when you're looking at infrared windows to look into chambers. You would need to know the transmittance of the glass in order to compensate for any, again, attenuation on there. The software that FLIR provides, you can input all of these parameters into the software. So these are not determined by the hardware. You can record the footage that you need, and all these factors can be changed afterwards. So you don't always need to know everything at the time of taking your measurements. You can calculate the emissivity and input all the other parameters later. There's just a short video here just showing a few examples. So this is a can of beer round about roomish temperature. So you would think if the can was the same temperature, you wouldn't be able to see the writing. But because the paint has slightly different material properties where the text is to what the image is behind, we can still see this is a difference of temperature. So the change in surface properties is a function of temperature as well. Effectively is a function of infrared radiation energy, but we see it as a change in temperature when we have that scale alongside it. When I played a video as well, I'm not sure they'll come across over Teams. It might be a little bit low frame rate, but at the top you will see the reflection, which is my hand spraying a cooling can, and you will see myself reflected just in the top of air where it's metallic and there isn't the matte finish sticker on the side of a can. So myself being a hot object will reflect off a IR reflective object as well. So if we just play that, I'll just give you an example of that. So this was actually taken with a cooled camera, so it gives a very nice, highly sensitive image there. So you can see the can being cooled. It's actually a dust spray can to get rid of dust out of keyboards, but it's with being aerosol, it produces quite a cold jet of air. So just let that play. Okay, so this brings us to if you're looking at a particular application, which type of camera would you go for? So the 4 factors here are kind of the main things you would look at. So the speed of the object, the size of the object, so this would be the smallest dimensions that you want to measure, and also the field of view that you would like to see, so basically your window. You'd also need to consider the sensitivity required. So this is not the terms of an absolute temperature measurement, but the smallest change in temperature that you would like to measure. So this is also called NETD, which is noise equivalent temperature difference. Sorry, just get a bit of water. And you also as well need to consider the rate of temperature change. So this brings us to the 2 main technologies. You have the what we call uncooled microbolometer cameras. An example on the screen there is the FLIR A700. and the cooled INSIB, or indium antimonide sensors. And as an example just there, so you saw those on the table that Matthew showed earlier. So that's the cooled photonic photonic detector. Okay, so now we'll talk about some of the advantages of cooled versus uncooled. So the way an uncooled camera works is it absorbs IR radiation, and this changes an electrical parameter. This is usually resistivity, and then obviously you can measure the voltage, and that change in voltage relates to a change in temperature. One advantage of these is that they operate at ambient temperatures, so you turn them on and they just work straight away. However, because you need to, in order to measure the voltage across a pixel, you need to bias that with a current, and any kind of electrical current will produce heat. So if you scanned the entire array at once, it will produce more heat, or sorry, more noise than what you would be able to measure. So what has to happen is that each line is scanned sequentially on the array. So what this does is it reduces integration time. Obviously, it takes time to individually scan. You've got to wait for enough energy to change the electrical parameter on each pixel. So this does take some time. So there's an integration time you need to consider. And because each line is going sequentially, if something's moving quickly, then when the first line is scanned compared to the last line, an object could have moved. And what you will get is a phenomena called thermal blur. And because it operates at ambient temperatures, it's subject to the usual kind of thermal and electrical noise you get with ambient temperatures as well. So you get greater noise and reduced sensitivity. The cooled photon detector cameras, so these look at the photoelectric emission of electrons in a semiconductor. So this will be electrons going from, if you've got a physics background, from the valence band to the conduction band, and kind of measuring the energy that it takes to get there. So very, very kind of complicated. You need a physics degree to understand that. But in simple terms, the sensor is cooled to minus 200 degrees, which reduces the thermal noise, practically eliminates that, so it makes them incredibly sensitive. But when you turn the camera on, excuse me, you do have to wait 10-15 minutes for the cameras to cool down. But once they're sorry, I just need a bit of water. But yeah, once they're up and running, they have a much faster integration time because of this. And what it allows it to do is that it has a global shutter. So what happens is all pixels can integrate simultaneously. So you don't get the thermal blur, or if there is thermal blur, it's going to be from frame to frame. But because of the cooled cameras can go up to, a kilohertz, 10 kilohertz, you can practically eliminate thermal blur in all but the fastest of applications. So this is the kind of technology where you can trace bullets, basically. And with the cooled sensor, you get the reduced noise and the greater sensitivity. So this is simplified, kind of like a visual to show what happens with each sensor there. So on the left-hand side, we've got the uncooled line scan. So hopefully this animation works. So yeah, you can see it goes line by line like this until a image is formed. The global shutter, you can see, scans every pixel at once. So I hope that should be clear. This is an example here of what can happen with the two different technologies. So on the left-hand side is with a cooled camera, and on the right-hand side is with an uncooled camera. And you can see on the bottom with the temperature versus time plot, you get a very different picture from what's happening. So the uncooled camera can give a misleading picture when it comes to the temperature because of the slower integration time. So if I allow that image to play, you will see that the uncooled camera has a basically the thermal blur on there. So I'll just play that now. So I hope that's coming through on the video. The two cameras it's actually pointed to in the video are no longer around. They've actually been replaced. I think the one on the left would be the X8580 now, and the one on the right is looks like it was a handheld camera, I believe. But anyway, but the it's still the same for any kind of the recent uncooled and cooled cameras. So an example here of the increased sensitivity with a cooled camera. So on the left-hand side, you can see, so this is a plant leaf, and you would expect it all to be this pretty much the similar temperature, you know, it's a homogeneous surface. But what you get revealed with a cooled camera is that even on a particularly homogeneous surface, the emissivity is still going to be slightly different from, you know, millimeter to millimeter. Nothing is completely the same emissivity. It's going to change its texture. So if something has texture, it's going to have difference. If you've got increased sensitivity, you can see that difference in texture. So on the right hand side there, we can actually see the, I guess it's cuticles on the leaves. I'm not a biologist at all, but you can see the substructure in the leaf, which is not visible with the A700. Another advantage of cooled cameras is that we can use spectral filtering. So Matthew mentioned first off that with the cooled cameras, there's some nice tricks we can do, such as gas visualization. But there's lots of things we can do. So I've got an electrical engineering background, so I always think of it as like tuning a radio in like the RF sense. So the cameras operate, the medium wave cameras operate between 1 to 5 microns. It's got the spectral range in the diagram there. But what we can do is we can tune that with low pass, high pass. We can do a band pass, or even what we call a notch or a band stop filter. And what this can allow us to do is to remove flames from footage, as it has on the right hand side there. So if you want to visualize more the particulates within a flame, or if they're obscuring something behind it, we can remove them from the picture. We can also measure the temperature of the flames by only focusing on that frequency as well. And there's various gases as well that only emit at very specific frequencies. So if you tune the camera to those frequencies, you can visualize those gases as well. But yeah, just to reiterate, it is only available for the cooled sensor cameras. Future webinars will spend more time on some of these features as well. So this is just a bit of a rundown here between the comparison between the uncooled and the cooled sensors. The main takeaway really, I think I've gone through them already. So this is a bit of a summary, so I won't go through them. But at the bottom there, you can see the difference in the triggering. The sync and trigger is only available for the cooled sensors. And this is because for precise synchronization, you need to take the image on the a very precise time. The uncooled sensors have a rolling acquisition. So if you trigger, you'll have to wait till it goes back to line 1, whereas the cooled camera can sit and wait for a signal, so it can be much more precise with its triggering. I think most of these features on there we've gone through already, but I'll be able to share these slides afterwards, and that will just provide a nice little summary. So we thought it'd be good as well just to go over some of the industries that we work in and just show some footage that we've done over the years. Unfortunately, a lot of the stuff we do is protected by NDA, so we're quite limited sometimes as to what we can show. But I've got some examples here of things that we've done. So some of the main industries working is electronics and semiconductors. So this is circuit board testing, component testing, looking for hotspots, general performance, basically just giving you the thermal information from the devices that you're testing. So if you need to account for cooling, or if certain circuits or certain devices are drawing more power, this will be reflected in the heat. We also do a lot with NDT and general materials testing. So this is looking at uniformity, defects in a composite material. We can see delamination as well. So if you heat from underneath, or if you flash heat at a material, the heat that's reflected or emitted from that, if there's a defect there, it will be different. And if a camera is sensitive enough, it will see that difference in the heat that's given off. We've also been doing a lot with the additive manufacturing industry. So this is often looking at melt pool temperatures. So for those who don't know, it's as the way I see it, it's 3D printing with metal, even with titanium and up to 1500 degrees. So, but it's very much a growing industry and being used to make a lot of aerospace and automotive parts. But we've been finding that the industry's found our cameras useful for measuring melt pool temperatures, cooling rates as the laser is passed over, and also looking at the spatter that's given off from powder bed welds. We've also been doing a lot with destructive battery testing, so observing thermal runaway, assessing performance of the batteries, and this has also led on to companies who are looking at different fire extinguisher agents, or just different strategies to putting out fires, and different protective materials as well. We've also launched, this will be a different webinar, but we've launched thermal vision ecology. So this is more focused on environmental studies. So we've been doing a lot with the ecology community, looking at bat surveys and any kind of like mammal and bird behavior. They use our cameras to kind of study population numbers, where they're roosting, and it can be used to see the effects of climate change and see what is affecting animals' behaviour. So with the PCB stuff, I said there'll be webinars that will go into this in more detail, but people often forget that well, maybe don't realise that although the thermal cameras have normal general purpose lens, they are also can be used as microscopes. So this is a PCB just off an old PC we had, and this microchip. Luckily for us, whatever the semiconductor material it was made of is partially transparent to IR, so we could actually see quite a lot of detail underneath the chip, so with the actual chip die itself. The first image is a 1x macro lens, field of view about 1.5 by 13 millimeters. So with this lens, with this field of view, the spatial resolution, which is effectively the size of each pixel, is about 20 micrometers. So we have a 1x macro lens, a 3x, and a 5x. So in the next slide, you'll see the 3x lens, which is the area that's been selected there. So that's the 3x lens. Again, it's a smaller field of view, but the spatial resolution is smaller. So you're going to see hotspots that you might not see with a wider angled lens. So if you're looking for a hotspot that's smaller than the pixel, it will be averaged out over that pixel. So you might not be seeing a peak temperature, you'll be seeing an average temperature. So you can only going to see these peak temperatures if you have enough pixels in that space. And with a microscope lens, looking at semiconductor devices, this is how you do that. So, for example, we worked with one customer who was looking at their microchip, and they was wondering why it was basically blowing up, and they couldn't understand it because it was only getting to 70 degrees. However, when they used the microscope lens on it and they had the resolution required, it was actually getting up to 170 degrees, which they wouldn't have known without the correct lens and the correct resolution for what they were looking at. So again, we can go really close. So this is the 5x lens, and this is only 1.9 by 1.5 millimeters. Here, the spatial resolution is around about 2 to 3 micrometers per pixel. I mean, with pixels, they do merge in together, and as a whole, there could be a whole webinar on how that works, the pitch of the pixels, but this is a very simplified way of looking at it, looking at a size per pixel. On the left-hand side there, it just gives you an example of what a setup might look like with a microscope lens. So the lens on there is the 5x lens. It's a bit of a beast. And the one next to it there is the 3x lens there, so it's slightly shorter. So the stand that's being used is a Thor Labs one, and it keeps it very stable. So you can imagine when you've got a very small field of view and it's very much zoomed in, any slight knock on the desk or movement in the office, even walking past it, can create vibration and wobble on there. What else have we got here? So we've got, this is some work we've done with basically NDT, observing how a material performs when heat is flashed on it. So here, it's like a laser pulse that's flashing on a piece of material. I have to keep the customers hidden. But you can see here, as it passes along, we see the gradient reduce. So they were looking at the peak temperature, how hot it was getting. and the heat source was being, obviously you can see it pulsing there. They wanted to change basically it's like a PWM, I believe, so like pulse width modulation. So they wanted to modulate that based on what temperature they were getting on the film that they were looking at. And on the right hand side here, this was an aluminium substrate with battery electrolyte on it, and it goes through a process of what they call calendering. And with this, because the rollers are heated, it actually does half a job for us. So it's applying the heat there. And where it's thicker, it's more insulated, and therefore the temperature will be lower on the surface. So we can see the kind of like a corrugated effect. So obviously there must be some rippling on that substrate, so it wasn't perfectly level. The customer actually knew it wasn't. It was actually a bad batch. So it was just a kind of proof concept that the camera would see that. But we're talking here something that's less than a couple of millimeters thick, so very much down to micron thickness. The cooled cameras can see the difference in uniformity in materials with heat applied there. Just an example of what we've done with battery testing. So this is a still of a battery about to go. But what we can do is, so on the right hand side there, you can see we've tracked a temperature, and we can see even through casing, we can observe the various fluctuations in the thermal runaway of what's going on with the battery. So this was by tracking the maximum temperature on there. I do need to discuss this with a customer to know exactly what's going on, but obviously this is characteristics of thermal runaway. Just a couple of our videos here of battery testing. So on the left-hand side here, this is with a long wave camera. And even without any filter, we can see through flame, and it removes most of the smoke. So this had 4 visual cameras in the same testing cell, and the room was completely engulfed in smoke, and the customer could not see what was going on at all. The only way they could see what was going on was with a thermal camera. If you look closely, you can see a nozzle there that's actually spraying on liquid nitrogen to put out the fire. It's done quite well on that one spot, but you can see it's not affecting much. So in this case, we can see the effects of the extinguishing agent on the fire and how it's spreading. Is it stopping the propagation? So we can do that with our cameras. This is just a very short video showing the delamination that we can see. So this is sped up a fair amount. I think the frame rate seems to be quite low because it may be playing on the other one. So I'll pause that one there. So again, this is a camera. This is a battery about to go into thermal runaway. This is actually a pouch cell as well. So let me go to the next one. So, right. Well, that's it. I thought there might have been one more. So just want to say thank you for everyone for joining us. It feels a bit weird doing this for my first webinar because I can't see anybody, so I feel like I'm talking to myself, but hopefully that was interesting. If you've got any questions, please ask, and any feedback as well would be really useful. As Matthew said, we're going to do some more webinars throughout the year, focusing on each what we think will be interesting features. But if you tell us what you think will be interesting, what you want to know more about, we can add these to future webinars as well. Again, as I said at the start, if you've got a specific application in your company or at your university that you think a thermal camera will be useful for, by all means, email us separately and we can kind of arrange a one-on-one call and a demonstration. So, yeah, I think that's all from me. Hopefully you're
Andy,
all
if we could
there.
just, if a moment, could we go back to the slide that shows the dots for the rolling shutter and then the global? I just wanted to just quickly mention something on that.
All right. Okay. Yeah, sure.
Awesome.
Is it still sharing, isn't it?
It's still sharing. Yeah, perfect. So if we just go back to.
Yeah, I was going to say, Matthew, you're the expert. So yeah, if I've missed anything, by all means.
If we just present that one, that's perfect.
All right, I'll have to just. All right, I think to do the animation, I'll just have to go back to and present it. So I think I'll do it from that one there. So yeah,
brilliant. Okay, thank you. So just to go back over, if you take anything from today's webinar, there is one thing that really is the difference between a cooled and uncooled camera. And it is this slide, really. So on the left, what it's showing is that the the sensor is reading the temperature, or is reading the heat from one row at a time. So if we say that this sensor has a 640 by 480 resolution, it starts at row 1, then row 2, then row 3, then row 4, and will work its way down. And it takes roughly 12 to 15, 20 milliseconds, depending on the type of camera. And that goes on forever. And you can't change it, and it's rolling round and it's rolling round. But of course, if you have an application that is, we would say, thermally dynamic. So what does thermally dynamic mean? So that could mean that it's fast. So for example, a bullet flying through the scene, or it could be a car moving through the scene, or it could be an object that actually heats up almost instantaneously. So for example, the moment you put power into a PCB board, you might want to understand, are there any hotspots on any of the components? So as you cycle the power on and off, on and off, on and off, you can actually build up hotspots. So if you imagine having a camera that only images one row at a time on a moving object. So let's say, for example, the bullet starts on row 1, and then you go to row 2 and it's disappeared, and then you see nothing. Not really very useful for us. Or if you have a car going through the scene, you've got row 1, which takes part of the car, and then but even at 20 milliseconds, by the time it gets to row 2, the car has actually moved a little bit. By the time it gets to row 3, it's gone. So you end up with this blurring, which is the image that Andy showed you a moment ago. But the one that's more important for a lot of people is, imagine your application is looking at something that's heating up almost instantaneously, or maybe over a couple of seconds, or let's say from 0 to 300 degrees. You start at row 1 and the temperature is 1 degree, and you get to row 480 and your object is now 60 degrees. When you get back to row 1, it's now 100 degrees. So row 1 has essentially gone from 1 to 100. And this is why sometimes you can get these funny graphs that appear to go up and down for something that actually is just heating up, because the sensor isn't fast enough to keep up with it. So the one thing to take away is that on the right-hand side, the cooled sensor is all frames, all pixels instantaneously. And this is temperature dependent, and we will get into this when we talk about the webinar about high-speed recording. But if you need something that is blur-free and instantaneous, then you have to go for the cooled camera, because it's all frames, it's all pixels instantaneously, irrespective of frame rate. All right, so we can get into that when we talk about our high-speed webinar. So maybe just a quick one for everybody now. Hopefully you enjoyed it. It's our first webinar, so hopefully it was good. So let's have some thumbs up if you think so. But if I have any questions, maybe just add them into the chat.
Yeah, I was going to say I'm not able to go into the chat, so I don't know if anybody else has been restricted from using the chat, Matthew.
Oh, okay.
I don't know if Jeffro, our tech guy, can address that. So maybe. So
we had something from Andreas. Thank you very much. We not as good as you, mate, but we tried for our first one. So is anybody else able to offer anything into the chat?
No, I don't have anything on mine, so.
Yeah, I can't send messages, Jeffro, so I'm not sure if people are not able to.
Well, so maybe if anybody wants to unmute and ask a question, we'll try and see what happens.
Yeah. I think you can put your hand up in Teams, so there's a little raise button. So.
Okay, we have Sam. Yeah.
Sam there. Yeah, Sam. So yeah, if you want to turn your microphone on.
The CO2 filters and the spectral filters, I know this might be a dumb question, but they're physical filters that fit on the front of the camera, or they are in software?
So the filters are, as you quite rightly say, they're physical filters, and they actually go inside the camera, and that's actually quite important. So on the big, for example, the premium camera, the X series camera, inside the camera is what we call a filter wheel. So you're able to fit 4 filters, but you can actually double stack them. So you can actually have 8 filters. So you put the filter in there. And one of the reasons for that is that they are thermally stabilized. So if the filter was on the outside of the lens, so for example, you have camera, lens, and filter, the filter will also be absorbing some heat from the surrounding, and that can affect the filter. So filters always internal, and we have different ways of fitting them. So some cameras have a filter wheel, and some cameras, they are literally screwed onto the back of the lens and then into it, but they're always inside the camera rather than being outside the camera, but they are physical objects.
Cool, thank you.
And what we can do, maybe, in fact, that's a really good point. I think what we'll do, webinar, I believe number 6, is I talk a little bit about filters. So what we'll do is we'll show you a filter wheel and actually how it's working. And if I'm able to, we'll do one that I have in my camera is a through flame filter, which actually is really amazing. So you can actually have a bonfire going. You have the camera looking at it and it's all saturated out. You put the filter through and you see straight through the flames as if they're not there. So I'll try and set up a mock of that to show you, but I'll show you how filter wheels are. So I'll make a note to definitely show you how to fit and use filters.
I think Shaibal had his hand up. Have you still got a question, Shaibal, if I'm saying your name correctly?
Yeah, I put my hand up because I wanted to speak about the filter, but that is actually next sessions would be what we're going to see. Actually, there are filter wheels and there are filters, and how to choose the proper filter for proper applications. I think so that also will get covered there, right?
Absolutely. So you're absolutely right. So there are lots of, how should we say, standard off-the-shelf filters. So for example, if you wanted so for example, if we're using a cooled camera and you're measuring plastic, so plastic, say a plastic film, with a cooled camera, you would see straight through it because it has a very high transparency. But you can actually have a filter that allows you to see just the surface of that material. So there are standard off-the-shelf filters that we can show you, but also you can buy your own filter. So for example, a cooled camera may have a wavelength of 1 to 5 micron, but let's say you want to understand what's happening when a laser at 2 microns is hitting a material, and you maybe very specifically need to look at the laser. So it could be that with a 1 to 5 camera, it's slightly too wide to see the laser. So what you would then do is we would help you then pick a filter that has a peak at 2 microns, but also a width. So, for example, we go to companies like Spectragon is a global company that do filters, and you can literally go onto their website and pick essentially a peak and a width. So, for example, you might be interested in a 2 micron laser, so the peak will be 2, but you might have a width of 0.5 either side of that, so that you gather a little bit. And then you have the full response of the camera in a very narrow band, so you can pick up a lot of detail in there. But it is something that we would help you do, and we can order the cameras through Spectragon, and also depending how deep you want to get into this, what we can also do is we can also do almost like we can do what's called a spectral response. So we can have the camera calibrated with that filter and then give you a graph of the response, i.e. how much performance the camera will give you with that particular filter. So within filters, there's a huge amount of detail that we can go into. But generally, our job is to help select the right camera, but also whatever you need to do that application. So whether that's filters or mounts and different things, but we would certainly help you with that.
I have, because it will be in the next session, just I want to add something there. If you see the FLIR, the LWIR cameras, for example, A650 SC, for example, they have a filter adapter for the long wave cameras, correct? And always the cooled cameras, yeah. So it will be good actually if you can place a slide. May not be a practical understanding. Most of the people, they try to understand, they want to spectrally adapt the long wave cameras with the filter adapter.
Yep.
Does that work? And what is the advantages of that? Number one.
Again,
number two.
Absolutely. So we have, so when Andrew talked about the different spectral ranges, so we have short wave, medium wave, and long wave. So cooled cameras work in all three bands, but microbolometers, the uncooled cameras, only work in long wave. But long wave cameras, even uncooled, can still have filters. So there's a camera that unfortunately is kind of been replaced by the new A700. So it's a camera called the A615 or A655. And you could actually buy a filter holder to go behind the lens. So I have this camera with a lens at Liverpool University where they're looking at lasers. So what they want to do is they want to protect the sensor from the energy of the laser. So they've put a filter in to essentially only accept energy at a particular wavelength in the long wave region, which is 7 to 14. If my memory serves, I think they had a band pass. It's like 8 to 9 or 8 to 10, which suited them. So we can have. It's essentially, you can have filters for any camera, whether it's cooled or uncooled, medium wave or long wave. The filter is simply application dependent, and we can help choose that.
Thank you.
All right, but we will go into filtering in more detail. And anybody else with any questions? I will be here for hours, so just to warn you, if you ask too many questions, I will just keep talking and talking.
I was going to say, yeah, if anyone's got any questions. Unfortunately, even Jeffrey says, I don't know what's happened to the chat. There's probably some box we've not ticked, but no one seems to be a member of the chat, which I'm not sure. I've never had that on Teams before, but obviously it's going to happen on our first webinar, isn't it? So I apologise for that. But if anybody else got any questions, just put your hand up. What I'll do is I'll share our contact details again, so you can always make a note of that and just send us a question through email and we can get back to you afterwards. So I'll just do that now.
Brilliant, well done. So awesome. So yeah, thank you very much. It's our first one. We've got 5 more to do, so hopefully you'll find it interesting. And again, our contact details will be obviously on the LinkedIn emails that we sent out. What we'll also do is we'll send an email to everybody. Oh, okay, sorry. So some people just have got kicked out of the webinar as well. So teething problems, which we'll sort for the next one. But we'll contact everybody. If you have any questions, please email us, call us. That's what we're here to do.
So yeah, let's any more questions. We should be wrapped up on time. But yeah, anybody else at all?
For say combustion applications, if you were looking at the combustion of fuel and wanted to, could you differentiate between like say CO2 and NO2 or CO and CO2 in a flame or in a discharge from that flame with filters, or is that too complex?
Well, there is individual filters for each one of those gases that FLIR provide. I've not used them, but as each one is if they're far enough apart on the spectrum, and you've got the CO2 filter on, you should only see the CO2, and the same for the N2O filter as well. I don't know if you've got a bit of experience with that, Matthew, but
yeah, fumes or gases are particularly difficult for cameras. Essentially, thermal cameras can't see gases, which is why we use the filters to do it. And in some cases, while we would normally use, so if we look at the wavelength of a camera, and if we look at a medium wave camera in the 1 to 5 or 3 to 5 region, we have a lot of contrast in that region. So it gives us a lot. So, for example, the images that you see on the screen here of myself and Andrew, they're really sharp. There's a lot of detail there because it's in the medium wave. There's a lot of information there for the camera to then process. In the long wave, there's less, but we are still able to see gases in the long wave. And it can be that sometimes a long wave camera is better than a medium wave camera. But again, for us, everything is, and also with gases, it can be sometimes down to things like parts per million. If it's a big, if it's a big discharge of gas, you might see it. But if it's a very, very small discharge of gas, it might be really difficult. But there are also filters and things that we can do in the software, like I completely lost. It's like so essentially we can take one frame and remove it from the next frame, then remove it from the next frame, then remove it from the next frame. And what you just see is you see differences between each frame. So that coupled with a filter can help. So sometimes with gases, it's a combination of the right camera, the right filter, and also using the software correctly. But what we normally say is everything is application dependent. We have lots of filters for different things. So generally what we say is, let's come and have a look. If it's something that you can recreate, let's do 3 or 4 filming, and then let's have a look at the data and see what we can see. But gases are a particularly interesting one. And if you're happy to email me and ask me about gases, I can send you a technical publication that we have that specifically talks about gases and the problems that arise with being able to image gases. It's not as easy as people think. But please just drop me an email and I can send that over to you.
Cool, thank you.
All right, perfect.
So, anybody else before we end the call? Any questions?
Cool. Okay.
And that's it. Then we'll be ending just about on time. So
brilliant.
Yeah. Thanks again for joining us, everyone. And thank you, Matthew, for your wealth of knowledge and experience.
Awesome. All right. Have a great day, everybody, and we'll see you for the next one.
Yeah. Thanks,
guys.